High-speed automated production lines push structural materials to their mechanical design limits every single second. When a machine jams or a line goes down, it rarely happens because of a single massive impact. The true cause is usually the invisible, long-term accumulation of structural fatigue. Take a rapid sorting system frame that has just suddenly suffered a catastrophic geometrical misalignment, stopping production entirely. To understand exactly why this jam occurred, we have to look past the visible break. We need to examine the microscopic crystalline structure of the failed steel joint. Solving this kind of engineering failure requires abandoning guesswork. It demands that we strictly calculate the mechanical laws of stress, strain, and material resilience. Structural integrity in manufacturing is governed by three quantifiable behaviors: elasticity, plasticity, and toughness. In engineering mechanics, these represent mathematically defined parameters that dictate how a material responds to external forces. These variables dictate everything from the necessary thickness of a steel support beam to the precise material selection required for high-stress dynamic applications. Mastering the exact boundary lines between these properties is the only way engineers can predict and prevent catastrophic structural misalignment before a machine is even built. Elasticity is a material's ability to perfectly recover its size and shape when force is removed. The specific property resisting this deflection is stiffness, critical for minimizing the sway of tool overhangs during rapid movement. Hooke's law states that for small deformations, applied load per unit area, stress, and resulting deformation per unit length, strain, are directly proportional. This constant ratio represents precise rigidity, known as Young's modulus. This can be broken down mathematically. Total elongation equals the load multiplied by the original length divided by the cross-sectional area multiplied by Young's modulus. By manipulating the cross-sectional area to keep operational stresses strictly within this linear elastic regime, the machinery will repeatedly return to its zero-state alignment. So what happens to the structural frame when an anomalous force, like a sudden load spike, pushes the material beyond Hooke's predictable linear zone? This chart shows the threshold where the linear relationship ends, defined as the elastic limit. This is the maximum stress a material can endure without permanent deformation. Once a frame breaches this, it enters the plastic zone. Even if the jam is cleared and load removed, the material won't fully recover. This unrecoverable gap is permanent set, the exact micromechanical shift that permanently misaligned our sorting line. The characteristic allowing a material to deform and flow under a load before rupturing is plasticity. Plastic flow takes two forms: malleability, yielding under compressive forces, and ductility, yielding under tensile forces. While high plasticity is necessary for forming the metal shapes initially, allowing any plastic flow during live cyclic operations causes immediate failure in precision machine alignment. Static, slow building loads represent a fraction of the forces at play. High-speed sorting environments involve continuous cyclic vibration and sudden shock impacts. The defense against this dynamic failure is toughness. This is defined as the total energy a material can absorb under force before fracturing entirely. This visualization shows toughness as the entire measurable area beneath the material's stress-strain curve. Toughness is distinct from hardness. Hardness is merely a material's localized capacity to resist surface penetration, abrasion, or cutting tools. This distinction reveals a common engineering trap. A frame built out of ultra-hard die steel can shatter because it lacks the toughness required to absorb high-frequency shocks. Structural resilience requires a calculated compromise: high enough stiffness to prevent elastic sway, paired with immense toughness to absorb sudden blows without initiating microfractures. Returning to the autopsy of the jammed conveyor line, we can now apply precise diagnostic terminology to explain its demise. The cross-sectional area of the joint was insufficient for the cyclic shock loads. This allowed peak stresses to repeatedly breach the elastic limit, accumulating a minute permanent set with every cycle. The corrective engineering action is to use the elongation formula to recalculate the exact cross-sectional area required to safely distribute that specific dynamic load. By increasing the structural area parameter, we lower the internal stress back into the safe, linear, elastic regime. Engineers achieve structural resilience by precisely matching material properties and geometric area against the calculated operational forces. Beneath the rigid appearance of heavy machinery, every physical structure on a production floor operates as a highly tensioned elastic spring. An automated system only remains functional as long as every rapid movement begins and ends strictly within its elastic limits. Preventing catastrophic factory downtime is an exercise in respecting the mathematical boundaries of Young's modulus and material toughness. By mastering these micromechanical laws, engineers can transition a facility from suffering unpredictable breakdowns into an era of flawless, predictable production.
Thank you for viewing so far. If it gives you some information, hit the like button and subscribe for more such technical learning.